Now that we've used a slope field to introduce the idea of a phase line, we're going to now show how you can use phase lines to create sketches of solutions. And again, these are very powerful qualitative techniques for analysis. And basically what we're going to do is we're going to use three things primarily here in these two examples. We're going to use the equilibrium points. This should not be a surprise, right? Let's, what is the name of this section if not talking about equilibrium? And then we're also going to use the uniqueness theorem, interestingly enough. From our previous section, we had some videos talking about why the uniqueness theorem matters, and now we have a section while we're using that uniqueness theorem. And finally, we're going to use some qualitative analysis on the derivative. All right. We're going to be thinking about, well, is dy dt positive? Is it negative? Is it big? Is it small? How do we know what it is? That information is not in the phase line, but we will be having the function itself. Okay, so these are the three things that we're going to use, and we're going to sketch some solutions using phase lines. So let's get started. We'll do two examples. The first one is I want you to sketch well, I'll help you, but we are going to sketch solutions to the differential equation dw dt equals 2 minus w times the sine of w. All right, and we're going to, this time I'm going to give you the phase line. I won't give you the phase line later, but I'll give it to you right now. And the phase line, again, it's always vertical lines. That's not true. I'm sure some books have it as horizontal lines, but our textbook has it as vertical lines. All right, so you do know the equilibrium points. You could find that yourself, but I'm giving you this phase line here. There's an equilibrium point at w equals 0, equilibrium point at w equals negative pi, negative 2 pi, negative 3 pi, and so on. There's also an equilibrium point at w equals, again, pi up here, but also at 2. Right? And specifically, I'm telling you that if we're above pi, the function's increasing. I'm going to use a different color. If we're between here, the function's decreasing. Between here, the function's increasing. And down here, decreasing. And up here, it is increasing. So there's the phase line. It's got the equilibrium points and has the direction of the function between each equilibrium point. All right. So what are solutions going to look like? Well, if we plot our axes, right? Oh wait, negatives actually do matter here. If we plot our axes over here, let's start by plotting those equilibrium. Let's do the equilibria in blue, right? So there's an equilibrium at pi, an equilibrium at 2, an equilibrium at 0, an equilibrium at negative pi, and we're going to have things happen between these. We have used, oops, that's supposed to be circling. We've used information about equilibrium points. Now we're going to use the uniqueness theorem. Remember, we said if a solution is unique, then essentially solutions aren't going to cross each other. That would break the uniqueness. So we know if we have some solution over here, it's going to be stuck. It's going to be trapped between these equilibrium solutions because it can't cross. And furthermore, if it's between here, we know it must be decreasing the whole time because of the phase line. Also, we know, right, let's label this, right? This is 2, this is pi, 0, this is negative pi. We also know it's decreasing because if it is between 2 and pi, right, then this part is negative and this part is positive. Negative times a positive is a negative. So we know the function's decreasing on that whole interval. All right, and then it'll be increasing in this whole interval and decreasing in this whole interval. Also, it is really important to label your axes, so I'm sorry for not doing that. Here we're saying, how does this function, this solution, change over time? And then, so we know they're going to be trapped. Now let's talk about the derivative itself. Again, in any of these intervals, let's just start in this chunk over here. where we know we're decreasing because of the phase line and because of the derivative. When is this biggest? When is the slope the biggest between here? Well, when w is close to 2, the slope is near 0. When w is close to pi, the slope is near 0. So it's like asymptotically between these two things. So, maybe we have some kind of solution that asymptotes, wait, it's decreasing. So asymptotes down to this one. And then maybe like asymptotes up to here. Maybe that's what a solution looks like in this chunk. Right, it's decreasing. The slope is near 0 when the w value is near 2. The slope is near 0 when the w value is near pi. Sorry, this is 2. This is a w value of 2. Slope is 0 means horizontal tangent line. And we could continue this with every single piece using very similar logic. Right? And in fact, we're going to have very, very, very similar things in each piece. Oops. All right. And then what you'll get is you'll get that a bunch of solutions kind of look like this. And you can see that these are a whole bunch of solutions. And of course, there's multiple solutions in each chunk, right? There could be another solution over here. And in fact, since it's autonomous, right, there's no t variable here, we know there's infinitely many horizontal translations of every solution, right? I could plot infinitely many solutions here. And remember, just because there's infinitely many solutions is not the same thing as saying we don't have uniqueness. For every initial condition, there's a unique solution. Each one of these curves just shows the solution for a different initial condition. All right, that is an important distinction. All right, let's do another example. Oh, as a side note, it's not a coincidence here, by the way. We'll talk more about this later. If you have an autonomous ODE with a continuously differentiable right-hand side, your functions are going to be monotonic. They'll only increase, they'll only decrease, and specifically, they'll increase up to equilibrium points or increase off to infinity without bound, and vice versa for decreasing. We'll talk more about that later. All right, so let's do kind of the same thing, but this time I just want you to draw one solution, and I'll have you practice. Draw a solution to the differential equation dp dt equals 1 minus p over 20 cubed times p over 5 minus 1 times p to the 7th. And I want you to try to do this on your own. Pause the video. Try to create your own phase line and your own solution sketch. See how far you can go, and then unpause it to get some hints if you need it, and then pause it again in the middle solution and see how much of this you can do on your own. Okay? All right, so let's start. We're going to start with our phase line. And to create a phase line, we're going to need equilibrium points. Equilibrium is the value, again, this is autonomous. This is going to be equilibrium points are going to be when each of these are 0, because that makes the whole thing 0, and then it's not changing. That's why it's equilibrium, right? It's staying there. So p is going to be 20. Equilibrium point when p is 5. And equilibrium point when p is 0. So equilibrium point at p equals 0. P equals 5. And p equals 20. All right, so now we have all of our equilibrium points. Now, this is something really exciting. We get to use the intermediate value theorem. If you remember the intermediate value theorem, we have like, oh, one thing is positive, one thing is negative. If we have a continuous function, then it must cross 0 between then. Well, similarly, if we know all the zeros, which we do, then something has to be, if something's positive in one place, it has to be positive everywhere in here. Because the only way it could have switched from positive was at a 0, but we have the zeros plotted all the way. So we know if it's increasing at one point here, it's increasing at all of them from the intermediate value theorem. And we know we have all the zeros, which in this case represent the equilibrium point. So that's pretty powerful. So we can just pick any point between 0 and 5, like p equals 1. If p equals 1, right, this is positive, this is negative, and this is positive. So if p equals 1, we have positive. The function's increasing here. If p is -1, right, this is positive. Yeah, just making sure I'm right. This is positive, this is still negative, and now this is negative. All right, so the whole thing is negative, which means the function is decreasing. If p is like 10, right, if p is 10, then what do we have? We have still positive, and still positive, positive. So it's increasing. And if p is like 40, oh, I didn't leave myself enough room. If p is like 40, right, then we have negative, positive, positive. So negative. And here again, we have this really nice thing, right, where it switches from negative to positive. Wait a minute. I think I made a mistake. If p is 10, wait. This one should be negative, right? If p is 1. If p is 1, it was positive times negative times positive. That's negative. And then that, yeah, I flipped these ones. Okay, great. Whew. Anyway, my point is, right, that here we have this nice alternating situation, but again, it doesn't have to be alternating. And we'll see examples where it's not alternating. And we'll talk about what that means for equilibria. Okay, so again, we're going to translate this phase line to a plot. So we'll graph the equilibrium solutions of p equals 0 is an equilibrium solution, p equals 5 is an equilibrium solution, and p equals 20 is an equilibrium solution. We're going to label our axes. All right, this is our dependent variable time. Sorry, independent variable time, dependent variable p, maybe a population. And again, similar to what we did before, we can make the exact same conclusions that we did before, but things will be pretty similar. We don't know exactly the shape, but we're going to have something pretty similar, right? We have this sort of behavior between these, slopes getting close to 0. We have uniqueness again, because the derivative of this, we'd have to use the product rule twice and the chain rule, and it'd be messy. But we do know this is a polynomial, so its derivative is going to be continuous. The derivative with respect to p is going to be continuous, so we have uniqueness. Because we have uniqueness, they can't cross these lines. And we're going to get something like very similar. So here's one solution. Again, you could have other solutions as well. And that's pretty much it for this video. That's how you can sketch some solutions. Again, here it only wanted one. You could have drawn more, looking like this. If you're curious of how you did, right, you could pull up your little calculator thing and find out, right? Let's change everything to y's, so I don't have to change all of this, right? But 1 minus y over 20 cubed times y over 5 minus 1 times y to the 7th. And then again, what are we doing? We're looking from y goes from like, I don't know, -3 to like 25 or something. And okay, this is maybe a little alarming. What did ours look like? We had equilibrium solutions at 25 and 0. Okay, I don't see that. I think it's just because it grows really, really rapidly. I think we're still fine, right? If we did at 20, yeah, all right, we do have an equilibrium solution there, right? At 5, we have an equilibrium solution. At 0, we have an equilibrium solution. And then again, within each one of these places, in each one of these places, okay, it's having a little bit of problems. Essentially, probably because the slopes are really, really big. But I think we're okay. All right, I'll double check and I'll let you know in the comments. That's pretty much it for this video. The next video, we're going to get more practice drawing phase lines and talk about different ways that we can create our phase lines. So it should be fun. See you later.